Welcome to an exciting journey into the cosmos. In this video, we're diving deep into the groundbreaking world of space exploration and discovery. Get ready to explore the wonders of the universe as we unveil the remarkable XRISM satellite. A powerful satellite called XRISM, X-ray Imaging and Spectroscopy Mission, is set to provide astronomers with a revolutionary look at the X-ray sky. XRISM, led by JAXA, Japan Aerospace Exploration Agency, in collaboration with NASA and with contributions from ESA, European Space Agency, is scheduled to launch on an H-IIA rocket from Japan's Tanegashima Space Center at 8:26 p.m. EDT on Sunday, August 27, 9:26 a.m. on Monday, August 28, in Japan. JAXA will stream the launch live on YouTube, with a broadcast in both English and Japanese starting at 7:55 p.m. EDT. Some of the things we hope to study with XRISM include the aftermath of stellar explosions and near-light-speed particle jets launched by supermassive black holes in the centers of galaxies, said Richard Kelley, NASA's XRISM principal investigator at NASA's Goddard Space Flight Center in Greenbelt, Maryland. But of course, we're most excited about all the unexpected phenomena XRISM will discover as it observes our cosmos. Also on this launch is JAXA's SLIM, Smart Lander for Investigating Moon, designed to demonstrate accurate, pinpoint, lunar landing techniques by a small explorer. NASA provided a laser retro-reflector array for SLIM, as both agencies cooperate in the international effort to further explore the Moon and, ultimately, human exploration of Mars. XRISM detects X-rays with energies ranging from 400 to 12,000 electron volts. For comparison, the energy of visible light is 2 to 3 electron volts. This range will provide astrophysicists with new information about some of the universe's hottest regions, largest structures, and objects with the strongest gravity. The mission has two instruments, Resolve and Extend. Resolve is a microcalorimeter spectrometer developed in collaboration between JAXA and NASA. When an X-ray hits Resolve's 6x6 pixel detector, its energy causes a tiny increase in temperature. By measuring each individual X-ray's energy, the instrument provides information about the source, such as its composition, motion, and physical state. To detect these tiny temperature changes, Resolve must operate at just a fraction of a degree above absolute zero. It reaches this state in orbit after a multi-stage mechanical cooling process inside a refrigerator-sized container of liquid helium. Resolve leverages technologies developed for previous X-ray missions like Suzaku and Hitomi, said Lillian Reichenthal, NASA's XRISM project manager at Goddard. It represents the culmination of years of collaborative work between JAXA, NASA, and other partners from around the globe. XRISM's second instrument, Extend, was developed by JAXA. It will give XRISM one of the largest fields of view of any X-ray imaging satellite flown to date, observing an area about 60% larger than the average apparent size of the full Moon. The images it collects will complement the data collected by Resolve. Each instrument is at the focus of an XMA X-ray mirror assembly designed and developed at Goddard. X-ray wavelengths are so short, they can pass straight between the atoms of the dish-shaped mirrors used to capture visible, infrared, and ultraviolet light. Instead, X-ray astronomers use nested curved mirrors turned on their sides. The X-rays skip off the surfaces like stones across a pond and into the detectors. Each of XRISM's Xmas houses hundreds of concentric, precisely shaped aluminum shells built in quadrants and assembled into a circle. In all, there are over 3,200 individual mirror segments in the two mirror assemblies. After launch, XRISM will begin a months-long calibration phase, during which Resolve will reach its operating temperature. Once XRISM begins collecting data, scientists will have the opportunity to propose sources for the mission to study, said Mihoko Yukida, an astrophysicist at Goddard and Johns Hopkins University in Baltimore who works for NASA's Guest Observer Facility for XRISM. Researchers from around the world will have access to the cutting-edge work XRISM will be doing. XRISM is a collaborative mission between JAXA and NASA, with participation by ESA. NASA's contribution includes science participation from the Canadian Space Agency. XRISM is a general-purpose X-ray observatory. Clusters of galaxies. Galaxy clusters are the largest gravitationally bound structures of our universe. Most of the normal matter is in the form of a hot, X-ray emitting gas that exists between the individual galaxies known as the intracluster medium. But what is the cosmic history of this medium? How does it assemble into such large-scale structures? How does it get heated to extreme temperatures of tens of millions of degrees? How do outflows from supermassive black holes and cluster-cluster mergers affect its dynamics on both large and small scales? What is the chemical composition of this gas and how do clusters get enriched by stars and supernovae across cosmic times? XRISM will make detailed measurements of these objects, characterizing the temperature, chemical makeup, and motions of the hot gas in clusters, providing decisive answers to these fundamental questions and revolutionizing our understanding of the formation and the evolution of the largest structures in our universe. Hot stars. Massive stars with tens of solar masses slowly lose mass through high-velocity winds, especially near the end of their lifetime. These gases include elements such as nitrogen, oxygen, and carbon, which go on to be the ingredients of future stars, planets, and even life itself. XRISM will measure the motions and elemental abundances of hot gases produced by the winds, witnessing how these stars supply essential materials to the cosmos. XRISM observations will be ideally suited to spatially extended sources such as supernova remnants, whose X-ray morphology is a complex interplay between plasma in various ionization states. High spectral resolution observations will allow astronomers to disentangle the components of the emission lines resulting from the thermal properties of the hot gas with those resulting from the bulk motion of the material expanding at thousands of kilometers per second. XRISM will make detailed measurements of the abundances of various elements synthesized in the supernova, a direct probe of the mechanism of the stellar explosion. Starbursts. A collection of stellar winds from massive stars and supernova explosions create a galaxy wind, which removes materials from the galaxy and, therefore, affects the evolution of the galaxy. But how do winds blow through galaxies? How far do winds travel? And what is the fate of hot winds? XRISM will measure the velocity of the hot winds, for the first time, to constrain the total energy of the winds driven by star formation. XRISM will also provide the metal contents of winds to trace how heavy materials are transported into intergalactic space. Black holes. Black holes, big and small, when actively accreting matter, can launch powerful winds from their accretion disks. In the case of the supermassive black holes in centers of galaxies, these outflows can carry massive amounts of mass and energy, potentially impacting gas and stars in the host galaxy. XRISM is uniquely suited to answer many critical questions about the origin and destiny of such black hole winds. Thanks to Resolve's high spectral resolution in the hard X-ray band and good effective area, scientists will be able to resolve the structure of absorption lines imprinted by these outflows onto the black hole disk radiation and determine their velocities, column densities, and ionization. Furthermore, if the absorption features reveal currently unknown any particular shapes, they could be used to determine what force is pushing the gas away from the black hole, answering the long-standing question of whether these winds are magnetically, radiatively, or thermally driven. High-mass X-ray binaries. High-mass X-ray binaries, which consist of a massive star and a compact object, provide the opportunity to study stellar winds as well as the binary mass transfer in great detail. In these systems, radiation from the accretion process around the compact object is X-raying the wind material. The wind material that is being accreted is complex, e.g., as characterized by its geometry, its ionization structure, possible clumping, and more. With its high spectral resolution, XRISM is exceptionally well suited for separating the X-ray signatures of different wind components and characterizing the binary accretion process. If you found this information valuable, don't forget to hit the like button, subscribe, and ring that notification bell so you never miss an update.